Okay, let's unpack this. Today, we're diving into some truly mind-boggling territory. We're talking scientifically backed scenarios for the end of the world, or, at least the end of life as we know it. Now, don't worry, this isn't about anything immediate. Instead, think of it as a journey into the deep future. We're exploring what the universe might have in store, from, localized cosmic events right up to the ultimate fate of everything. You sent us some fascinating sources, and our mission to explore these ultimate cosmic threats. Things like gamma ray bursts, rogue black holes, the death of our sun, even the end of the universe itself. We'll try to break them down into simple, understandable terms. Get ready for some serious aha moments about the grand cosmic clock.
It's fascinating, isn't it? Because when you hear end of the world, you often picture immediate disaster. But science gives us this much broader view, a huge range of possibilities. Some are relatively sudden but incredibly rare. Others, truly inevitable, playing out over billions, even trillions of years.
Mhm.
So we'll look at the physics behind these things, their potential implications,
Yeah.
helping us understand not just what could happen, but maybe why it matters, even if it's way beyond our lifetime. The real insight, I think, is grasping the sheer scale of cosmic time and how our existence right now is in this remarkably stable but, yeah, fleeting window.
Okay, first up, something incredibly powerful. Sounds like pure sci-fi. Gamma ray bursts, GRBs, these are the most powerful explosions in the entire universe. I mean, the energy release is quoted as 10 to the 30 ergs on average. That's just
Yeah.
staggering. More energy in seconds than our sun's whole life.
It really is immense. Yeah, GRBs are typically the final catastrophic stages for massive stars. Things like Wolf-Rayet stars, these incredibly hot, bright giants when their cores collapse. Or they can happen when binary systems merge, like two neutron stars spiraling into each other. Neutron stars being those super dense remnants of old stars. And this process just unleashes this incredible beam of hard gamma rays, highly focused, high-energy radiation.
And it's not just one type of event, is it? The sources mention different kinds, and presumably some are more dangerous than others.
Precisely. Yeah, the biggest threat
Hmm.
potentially comes from what we call long GRBs. They're tied to those massive star core collapses and can last longer than, say, 4 seconds. Then you've got short GRBs, usually for neutron star mergers. They happen more often, maybe 5 times more frequently. But they're generally thought to be a bit less dangerous, shorter duration, maybe wider beams. And the least threatening, low luminosity GRBs. They seem to be linked to magnetars, those neutron stars with incredibly strong magnetic fields.
Okay, so incredibly powerful stuff. But here's the kicker. Has Earth ever actually, felt the effects of one of these in the distant past?
That's a really important question. And the sources suggest, yes, Earth has likely been exposed to GRBs before, and potentially with enough force to trigger mass extinctions. The standout example is about 450 million years ago. There's a hypothesis that a GRB contributed to the second largest extinction event in Earth's history, wiped out over 80% of species. And it wasn't like a direct zap, more like a devastating chain reaction in the environment.
A chain reaction. How does that work? How does a blast of gamma rays from light years away cause a mass extinction here?
Right, so the gamma radiation itself is nasty, obviously. It can ionize atoms, cause direct biological damage. But the bigger, more pervasive threat, that comes from how it interacts with our atmosphere. It basically rips apart oxygen and nitrogen molecules, leading to the rapid formation of nitrogen oxides. And these nitrogen oxides, they chew up ozone. So you'd see significant damage to our ozone layer.
Ah, our shield against UV.
Exactly. Our vital shield against the sun's harmful ultraviolet radiation. Without it, UV levels at the surface would skyrocket, devastating life. And on top of that, those nitrogen oxides could form a dense smog, blocking sunlight. That could potentially trigger a sudden global cooling, maybe even an ice age. And that sequence is what some scientists think might link to that extinction 450 million years ago, where about two-thirds of all animals vanished. It really makes you appreciate all that boring empty space between us and potentially dangerous stars, doesn't it?
That is a chilling thought. Seriously. But okay, what about now? What are the chances of that happening again? Should we be actively worried today?
Fortunately, no. For the current era, GRBs of any kind really don't pose a direct threat to life on Earth. I mean, we detect GRBs almost daily with telescopes. Observatories are constantly monitoring them. But the probability of one happening close enough to be lethal, say a short GRB within 10 parsecs, that's about 32, 33 light years, it's just incredibly low, vanishingly small. The sheer vastness of space is our best defense here. It's like winning a cosmic lottery, and we've been very lucky so far.
And this idea, connecting it to the bigger picture, that these bursts might sterilize huge chunks of the cosmos, That really feeds into the Fermi paradox, doesn't it? Why haven't we found anyone else?
It absolutely does, yeah, broadening the view. Some research suggests these powerful bursts could effectively prevent complex life from developing in maybe as much as 90% of galaxies, making only about 10% of galaxies truly safe harbors for life over long timescales. So it offers this potential partial explanation for the Fermi paradox, the big question of where is everybody?
Mm.
It suggests the universe might be a lot more hostile, actively pruning life in many places.
Okay, from these explosive bursts, let's shift gears. Let's talk about silent giants, black holes. Specifically, this idea of a rogue black hole just wandering through space.
Yeah.
Sounds terrifying, right? But what are the actual odds of Earth having a catastrophic run-in?
Right, the rogue black hole scenario. The chances of Earth actually being destroyed by one, they are, to put it mildly, astronomically small. Like infinitesimally close to zero. Not quite zero, but incredibly unlikely. The universe is just so vast and mostly empty. And stellar mass black holes, the kind left over from massive stars, they're actually tiny objects, typically maybe only 10 kilometers across. That's smaller than our moon. Think of finding a single specific tiny invisible pellet in an unimaginably huge volume of space.
Okay, so tiny target. But if one did get close, what would actually happen? Is it just getting sucked in? What's the main danger?
Yeah, getting sucked in a direct hit is extraordinarily unlikely. The event horizon, the point of no return, is very small for these stellar mass ones.
Yeah.
If one just passed nearby the solar system, the main effect would be gravitational. It would mess with the orbits of planets, could fling some out into space, pull others into weird elliptical paths, maybe capture a moon or two.
So chaos, but not necessarily swallowing Earth whole.
Exactly. Now, if it passed through the solar system, that's more serious. Major orbital disruption. It might engulf something or pull planets into its own orbit. But again, the odds of even that, let alone a direct hit on Earth, are extremely low. I mean, the nearest known stellar black hole, Gaia BH1, is like 1,560 light years away. There's a rough estimate, maybe one undetected one could be within 50 light years. But black holes are rare, maybe 0.0005% of stars in the Milky Way. And space is huge, so yeah, exceedingly remote chance. But what about the supermassive ones, the monsters at the centers of galaxies? Like, our galaxy's heading for Andromeda. Doesn't Andromeda have a huge one? Ah, yes, the galactic scale. Good point. Our Milky Way is on a collision course with Andromeda, expected in about 5 billion years. And yes, Andromeda has a supermassive black hole, maybe 100 million times the mass of our sun. It's a beast.
Yeah.
But even its event horizon is only about the size of Jupiter's orbit. So when the galaxies merge, and NASA and others stress this individual, stars and planets are still incredibly far apart. Direct collisions between stars are extremely unlikely, let alone a star hitting that tiny event horizon.
So even during a galactic merger, space is mostly space.
Pretty much. The supermassive black hole might drift through what was our galaxy, disrupting lots of orbits, definitely stirring things up, gobbling gas and dust, but directly eating specific stars or planets. Highly improbable, especially given the high speeds involved during the merger. The real takeaway is just how empty galaxies actually are on a star-to-star level.
That is reassuring, that sheer emptiness being a shield. But okay, theoretical chances aside, have we ever actually seen one of these rogue black holes?
That's a crucial point, because theory is one thing, observation is another. And yes, we have. In 2022, astronomers announced the first confirmed detection of a lone, rogue, stellar mass black hole. Its designation is MOA 111901 OGLE 110462. Bit of a mouthful. It's about 7 times the mass of the sun, and it's zipping through space at around 45 kilometers per second. So this discovery proves they exist, which is huge. But it also highlights how hard they are to spot and just how much space there is for them to wander through. Underscores why encounters are so rare.
All right, so rogue black holes, GRBs, incredibly unlikely to get us anytime soon. Phew, that's good news. But now we turn to something, well, much closer to home, and something we know is going to happen eventually, the deaths of our own sun. This raises the unavoidable question, what's that endgame going to look like for Earth?
Yeah, this is one of the truly inevitable scenarios, scientifically speaking, at least for our planet in its current form. Our sun's currently in its main sequence phase, right? Stably burning hydrogen. It's about halfway through its roughly 10 billion year lifespan, but crucially its luminosity, its brightness and heat is slowly but steadily increasing. In about, a billion years from now, the sun will have heated up so much that Earth will effectively move out of the habitable zone.
Yeah.
Surface temperatures will soar, oceans will likely boil away. Life, as we know it, just becomes impossible.
A billion years.
Mm-hmm.
Sounds like forever, but cosmically it's not. What happens to Earth in the lead up to that?
Well, over the hundreds of millions of years before that 1 billion year mark, Earth will go through massive changes. Its axial tilt will shift, the atmosphere's chemistry will change, CO2 levels will drop, then oxygen will likely decrease too, the basic conditions for life will degrade. Then, around that billion-year point, the intense solar radiation will probably start stripping away our atmosphere altogether. And then, fast forward to about 5 billion years from now. The sun runs out of hydrogen fuel in its core and starts fusing helium. It becomes a red giant.
The big expansion phase.
Exactly. It will swell up dramatically. It'll definitely engulf Mercury, almost certainly Venus too, Earth. We might technically avoid being swallowed whole, maybe. The orbit might shift outward slightly, but it'll be incredibly hot. Any remaining atmosphere will be blasted away. The surface might even melt, utterly uninhabitable. Even Mars will likely be toast by then, either too hot or right on the edge. The deep insight here, I think, is that humanity is just now starting to grasp its ultimate biological deadline, and the sheer scale of the project needed to even think about escaping it.
So this one really is inescapable then. We can't stop the sun becoming a red giant.
No, we can't. On these timescales, billions of years, influencing stellar evolution is way beyond anything we can realistically conceive.
Yeah.
So really, the only conceivable way for humanity, or whatever humanity becomes, to survive this specific endgame is migration. It's not about stopping it. It's about getting out of the way.
Migration. Okay. Where to? Finding a new Earth somewhere else.
Precisely. Yeah, the focus has to shift to finding and eventually colonizing suitable exoplanets, planets orbiting other stars. Ideally, you look for stars much longer lived than our sun. Red dwarf stars are the prime candidates. They're smaller, cooler, dimmer, but they've been burned stably for trillions of years, potentially. You need a planet in the red dwarf's habitable zone, stable orbit, Earth-like conditions. You know, magnetic field, atmosphere, maybe plate tectonics, the right chemistry, the whole checklist.
That sounds like, well, a ridiculously huge undertaking. What tech would we even need? How far off is that?
Oh, incredibly far off from where we stand today. You could break it down, maybe. First, you need really advanced telescopes and methods to find these perfect candidate planets. That could be decades, maybe centuries away. We're getting better fast, but there's a way to go. Second, interstellar travel. Actually getting there. That's the really huge hurdle. Probably needs hundreds, for likely thousands of years of advancement. New physics, maybe.
Yeah, warp drive stuff.
Right, or generation ships, or something equally exotic.
Yeah.
And finally, maybe genetic modification tech to help us adapt to slightly different conditions. That's developing fast now, could be practical in decades to a century if needed, but huge ethical questions there, obviously. We know of a few potentially Earth-sized planets in habitable zones, some around red dwarfs, some around sun-like stars. But getting there, still firmly science fiction for now. Imagine trying to tell your descendants hundreds of generations down the line that their survival hinges on finishing a journey started millennia ago.
It's humbling.
Humbling.
Okay, wow. So we've run from GRBs, dodged black holes, maybe even packed our bags to leave before the sun dies. But even those new stars, red dwarfs included, they won't last forever, right? Eventually they die too. So what then? What's the ultimate, truly, truly inescapable end for, well, everything?
Right. Now we're talking the grandest scale, the death of the universe itself. And the time scales here just become almost meaningless to us. Trillions, quadrillions, quintillions of years, maybe vastly longer. But eventually, yes, all stars will burn out. Even the longest-lived red dwarfs will finally fade after maybe 10 trillion years, 10,012 years. Galaxies will cool. Star formation stops entirely once the gas runs out. At that point, there are no new places for life to arise, no natural energy sources left to sustain anything complex.
So no more stars, just cold, dark emptiness. Is that the heat death scenario you hear about?
That's the leading contender, yes. Often called the heat death or the big freeze. And connecting it to the bigger picture, the idea is the universe reaches maximum entropy, maximum disorder. All energy gets evenly spread out. You reach thermodynamic equilibrium, uniform temperature, no energy flows, no work can be done.
Yeah.
And because of dark energy, this mysterious force accelerating the expansion, distant galaxies keep receding faster and faster. Eventually, they disappear beyond our observable horizon. Then over truly unimaginable timescales, maybe 10 to the 100 years, a Google years, or more, even protons might decay. Black holes evaporate via Hawking radiation. And what's left? Just a cold, dark, infinitely expanding void, filled with stray photons, neutrinos, maybe electrons and positrons. No structure, no complexity, no processes. Just stillness, the ultimate cosmic quiet.
That is profoundly bleak. Are there any other ways it could go? Other scientific possibilities for the absolute end?
Yes, there are a few other intriguing theories, though maybe less likely based on current data. One is the Big Rip. If dark energy gets stronger over time, it could eventually overcome all other forces. It wouldn't just push galaxies apart, it could eventually tear apart galaxies themselves, then solar systems, planets, even atoms, and finally the fabric of space-time. Potentially quite soon, cosmically, maybe billions of years in extreme models, but complex and less favored.
Yikes.
Then there's the opposite, the big crunch. This is more of a cyclic idea. If dark energy weakens or reverses, gravity might eventually win out. The expansion stops, reverses, everything collapses back together. Galaxies collide, temperatures soar, ending in a singularity. Maybe, just maybe, triggering a new Big Bang, a cosmic reset.
Like a bouncing universe.
Sort of, yeah. Then there's Roger Penrose's idea, conformal cyclic cosmology. It's a bit mind-bending. He suggests that after the heat death, when everything is just decayed particles and photons, the universe becomes geometrically simple in a specific way, conformally invariant. And this final state could mathematically transform or map onto the initial state of a new universe, a new Big Bang, an endless sequence of cosmic eons.
Whoa.
And finally, perhaps the weirdest one, vacuum decay. This proposes our universe's current vacuum state isn't truly stable, it's metastable. Like a ball balanced precariously on a hilltop, not settled in the valley floor. A random quantum fluctuation could, theoretically, trigger a sudden shift to a true vacuum state, a lower energy state. This bubble of new vacuum, with potentially different laws of physics, would expand at the speed of light. Everything it encounters, us atoms, everything would instantly transition into this new state. No warning, no escape. Our universe as we know it, just instantly replaced.
Okay, so for these ultimate ends, heat death, big rip, big crunch, vacuum decay, there's really no escape hatch, no prevention, no matter how advanced we get.
That seems to be the current scientific understanding, yes. On these truly cosmic scales, human intervention or even escape just doesn't seem feasible. Even wild ideas like time travel or jump into other universes, they aren't seen as realistic ways for a civilization to survive the end of its own fundamental reality. The physics we currently understand suggests that for the universe itself, and therefore for anything living within it, an end is indeed inevitable. That's kind of the ultimate aha moment, isn't it? The realization of absolute cosmic finality.
Wow. Well, that was certainly a journey right to the end of all things, and maybe even beyond, in theory. We've covered swift, terrifying gamma-ray bursts possibly shaping Earth's past, the slow, certain demise of our own sun, and these truly mind-bending ultimate ends for the entire universe.
What really stands out, I think, is just the sheer scale, both time and space. While some of these things might have impacted the past and others are definitely coming, eventually. The good news. For the foreseeable future, millions, even billions of years, our planet seems remarkably resilient and safe from these major cosmic catastrophes. It really encourages you to think critically about what immediate threat actually means in the grand scheme of things. It highlights our current precious stability.
Absolutely. And it also strangely highlights human curiosity and ingenuity, even thinking about solutions that are centuries or millennia away. So what does this all mean for you, listening? Maybe it's just a reminder to appreciate this amazing blue planet right here, right now, and to keep looking up at the stars with curiosity, knowing there's always so much more to learn, and maybe so much to protect right here in our cosmic neighborhood. Until next time, keep looking up and keep diving deep.
And perhaps a final thought to leave you with. Considering these vast timescales, these cosmic eventualities, does knowing about the inevitable end of our sun, or even the universe, change how you view humanity's current challenges, our efforts to sustain life right here, right now on Earth?